right? And the extreme value theorem was simply, how do you find the highest and the lowest point, right? And you check your endpoints, that's the first thing you do. And then you have to see, well, could you have a max, could you have a peak or a valley somewhere in the middle? And so we introduced this idea of a critical value. And a critical value is where your derivative was 0 or undefined. So you had to check those because those were your turning points. Today, we're going to talk about something called the first derivative test. And here's a big shock. Guess what you do? You take the first derivative, right? We're not really creative when we name things. So, and actually, before I talk about the first derivative test, I want to give you the big picture of what we're doing. Then the big picture of what we're doing is curve sketching. Like, how do you graph a function, right? See, right now, the way that you graph a function is you plot a bunch of points, right? That's pretty much the way you know how to do it. You could, I mean, like if I gave you some ugly polynomial, you could plot 5, maybe 10 or 15 points, and that might get you an accurate picture. If you use a graphing calculator, it plots 94 dots. If you put 94 dots in an area, then it's going to look like they're all connected, so that's how you get your picture, right? But plotting out a bunch of dots is not very efficient. So here's the argument. If I wanted to graph something, right, and I told you had a couple of dots, I said, let's say that the graph passes through those 2 points, right? Well, that's not really telling you a whole lot. I mean, it could look a whole lot. But if I tell you this is a flat spot and this is a flat spot, right? That's giving me some more information. And even better, what if I told you that we're increasing to this dot, decreasing to this dot, and then increasing? And then I end up with a picture that looks kind of like this, right? So this is kind of a complicated picture, but I technically only had to plot 2 points. But those 2 points had to be important. Those 2 points had to be significant as far as the picture goes. And so I plotted those 2 points, and I had some information, and I was able to create the graph without a whole lot of tedious stuff, right? And that's kind of where we're going, right? How do you graph something? You're still going to have to plot points, but you don't plot random points. You plot points that have meaning. And how do we find them? Well, here. So we're going to start with a function, because we always start with a function. So I'm going to start with f of x is equal to x cubed minus 3 over 2x squared. Now, as far as your first derivative test goes, there's going to be two things we're going to be doing today. The first thing I'm going to be interested in is I want to find out where the function's increasing or decreasing. And the next question, we're going to do a couple of problems with that. Then the next question we're going to ask is, where are your local max and local mins, or your peaks and valleys, right? And believe it or not, with those 2 pieces of information, that makes it where we can graph a whole lot of stuff. So, if I want to find out where my function's increasing or decreasing, the most important thing to find out where my function's increasing or decreasing is I need to find the flat spots. Because think about a graph. If it's increasing and then it goes to decreasing, what happened right before it went from increasing to decreasing?
It went flat.
You had a flat spot, right? Right? Or if you were decreasing to increasing, what happened right before? It was a flat spot, right? Or a flat spot or a cusp, but we'll just do flat spots. And how do we find flat spots?
Take derivative equals 0.
You take the derivative and set it equal to 0. We find our critical values, right? So, what I'm going to do is take the derivative, and so that's going to give me 3x squared minus 3x, and set it equal to 0. All right, well, I can solve that. I'll factor 3x out. That gives me x minus 1. And when I find my critical values, my critical values are at x equals, 0 and 1. Is everybody okay with that? What I've got is, I know my critical values are at 0 and 1, which means, those are my flat spots. So how does that help me figure out where things are increasing or decreasing? Well, these are our critical values. These are the only places that the function changes direction, right? And since 0 and 1 are the only places where my function changes direction, I'm going to kind of use that information to figure out where things are increasing or decreasing, and here's how I do that. I'm I'm going to draw a number line. And on my number line, I have 0 and 1. And my claim is, since I have a flat spot at x equals 0 and I have a flat spot at x equals 1, my claim is anything below 0, anything in this interval is either increasing or decreasing. Right? Because if there was another spot where it changed from increasing or decreasing, I would have another critical value. And since these are my only critical values, everything on this side is either increasing or decreasing. I forgot to talk about this. So wait, how does derivative, so how does knowing the derivative help us figure out if something's increasing or decreasing? Well, let's look at a picture. Right? What's my derivative here?
0.
0. What's my derivative here?
0.
That's easy. What's my derivative here? Is it positive or negative?
Negative.
Slope of the tangent line. What's my slope of the tangent line?
Positive.
Positive. What's my slope of the tangent line here?
Positive.
Positive. What's my slope of the tangent line here?
Positive.
Positive. Do you see if your function's increasing, then your derivative is positive? Right? And similarly, if the slope of the tangent line is if the slope of the line is negative, do you see the function's decreasing? So if the function's decreasing, then my derivative's negative. Or if we flip that around, if your derivative's positive, what does that tell you about the function? It's going up. If the derivative's negative, what does that tell you about the function? It's going decreasing. Question? Yes. All right. So my claim, yes.
So out of flat spot, how do you know that it's going to change from increasing to decreasing?
You don't. But if you're going from increasing to decreasing, there's probably a flat spot in between, right? So these are places where things can change direction.
Okay.
Right? Now, so what I need to have happen is I got to figure out what's going on with the graph. And how I know what's going on with the graph is I look at the derivative. And I'm going to check this interval. So I'm going to pick a number in this interval. So if I pick a number in this interval, some people say -1. I'm kind of obnoxious. I pick -1,000. Now if I pick -1,000, I'm going to go look at my derivative. And if I say -1,000 times 3, is that a positive or a negative number?
Negative.
Negative. -1,000 minus 1, is that positive or negative?
Negative.
Negative. Negative times negative is positive. And since my derivative is, so everything in this interval is going to behave the same way, meaning if one part's increasing, they're all increasing. So if my derivative is positive, what that tells me is my function is increasing. Right? So now I want to know, what is my function doing in this interval? Well, so I pick a value. Pick 1/2. Well, let's see. 3 times 1/2. Okay, that's positive. We're okay, 1/2 minus 1 is negative. Positive times negative is negative. So if my derivative is negative, what does that tell me about my function?
Decreasing.
It's decreasing, so I'll draw an arrow going down. And then I want to check a value over here. Right? So to check a value over here, pick 1,000. I always pick extreme values. Because anytime you can pick extreme values, it actually makes your life easier, because you don't care what the value is. You want to know if it's positive or negative. And it's easier to determine if something's positive or negative if you pick an extreme value. So 3 times 1,000, well, I know that's positive. 1,000 minus 1, I know that's positive. And so everybody's positive. And since the derivative is positive, that means my function's increasing. Right? This is called a first derivative chart. The reason I call this a first derivative chart is I got all this information from using my first derivative. Right? I like this chart. See, this little chart with some pluses and minuses and some arrows, can you almost see what the graph looks like? If you just look at the arrows, can you see that the graph is going to do this? Yes.
If one of the zeros is the multiplicity, you can see would the signs be the same?
Yes. Okay. But do you see how useful that chart is? Not only that, I mean, first I haven't graphed the picture, right? I've done no work to graph the picture. But does this graph have a maximum, a local max? Does it have a peak? Pretty obvious, isn't it? Does this have a local minimum? It's pretty obvious, right? See all that information we got from the chart? I mean, drawing this chart is huge. Okay, I'll talk about why. All right, so back to my question. Given this function, the original question is, where is this thing give me the intervals of increasing or decreasing. So where is this increasing and where is this decreasing? Well, where is it increasing?
Negative infinity to 0.
Negative infinity to 0. And then, well, then 1 to infinity. And it's decreasing from 0 to 1. Is everybody okay with that?
Is there any like mathematical way to write increasing or decreasing? Or
No.
That's fine.
Yeah. Now, I do have a little issue. So does everybody understand why I use an open parentheses? I don't include 0 as far as the increasing or the decreasing, because what's actually happening at 0?
It's flat.
Flat, right? It's not going up or down, right? So I think officially when you talk about things increasing or decreasing, you should use open intervals. Unfortunately, the AP exam doesn't think that way. Right? They actually ask questions. They'll give a function and like it's a multiple choice question, and they'll give you a function and they'll say, where is this function decreasing? Right? And so they would say, well, if you were given this problem, you would say, well, 0 to 1. Well, none of the answers will be 0 to 1 with a parentheses. Whenever they give intervals for asking where something's increasing or decreasing on the AP exam, they use closed brackets, which I don't agree with, but they never have a question that's use open parentheses. All the choices have closed brackets.
Why?
I don't know. They didn't ask me. I don't agree with it, but I'm trying to get ready for the test. So, all right. So what did we do? We had a function. We found the critical values. We made a chart. All right. I love the chart. It's not hard to create the chart, and when you create the chart, it gives you an idea of what the graph looks like. So let's try it again. So we give you f of x is equal to 3x to the 4th minus 4x cubed minus 12x squared plus 5. I want you to find the intervals of increasing and decreasing. So what do you do first? Take the derivative. Got to find our critical values. So I want to take the derivative. That's going to give me 12x cubed minus 12x squared minus 24x. And I want to set that equal to 0. So I'll factor out a 12x, which gives me x squared minus x minus 2. Which gives me 12x times x minus 2 times x plus 1. So what are my critical values? 0, -1, and 2. Now with my critical values, now I'm going to do my first derivative chart. I draw a number line and just got to make sure I put all the stuff in the right spot. And now that's taken my number line and it's divided into 4 intervals. This one, this one, this one, this one. And we've got to check to find out, what the intervals are doing. So I'm going to pick a value over here. Negative big number. So if I pick negative big number, well, let's see. Negative 1,000, this is negative 1,000 minus 2, that's negative 1,000 plus 1, that's negative. This whole thing's negative. And so if the derivative's negative, that means my function's decreasing. Next, I want to pick a value in here, so negative 1/2. Well, this is still negative. Negative 1/2 minus 2, that's negative. But negative 1/2 plus 1 is positive, so negative times negative is positive. This is positive, so I know this is increasing. And I'll pick a value between 0 and 2. I'll pick 1. So let's see, this will be positive. This is still negative, and that's positive. And so we end up with this is negative. That's decreasing. Then I pick positive big number, and everybody's positive. And so that's increasing. I mean, if you look at this chart, can you see what this graph is going to look like? Just by looking at the arrows? Can you see it's going to create a little W? Right? That's pretty easy, isn't it, right? I mean, with this little chart, it's really easy to say, okay, this is what the shape of the graph looks like. So let's just sort of answer the questions, and the questions are, I want to know where is this increasing and where is this decreasing? And well, it's really not much of a question now, is it? Because if you have this chart, you just look at the chart. Where is it increasing? It's increasing from -1 to 0, and it's increasing from 2 to infinity. And if I look at where is it decreasing, again, not much of a question. It's from -infinity to -1, and then from 0 to 2. Really like the chart. So now I need to tell you why why I'm having to stress that I really like the chart. So about 20 years ago, the AP exam decided that charts, they will not let you use charts for explanations, which I think is ridiculous. Because is it hard to create the chart?
No.
It's pretty easy, isn't it? Right? I mean, you basically draw a number line, right? Check a few numbers, right? We figure out, we get our little arrows. And not only is it, we can also look at this. I mean, we could easily identify. Okay, there's a valley, there's a peak, right? That chart is incredibly helpful. But 20 years ago, they decided, and I can tell you the logic why. They decided that charts were no longer a valid reason. Like, there are free response questions that kind of look like this. I mean, they have a bunch of parts, and maybe part A is find a local maximum. Well, okay, what x value causes a local max? What causes a peak? Local max is a peak. Based on this chart, where do you have a local max?
0.
At 0. Right? It's easy, right? Like if you look at the chart and I say, well, why do you have a local max? You go, well, duh, right? There's a peak, right? But now the AP exam actually requires you to do something else other than the chart to justify that that's a local max. I'll talk about that justification later. Today I'm just going to talk about the chart. And what I want, I want you to draw the chart. It's easy and it gives you a lot of information. All right. So you have to know where does something increase. We have to figure out, given a function, how do you find out where the intervals of increase or decrease? Okay, we found them. The other thing we have to find is they're called local max and local min.
Do you want the coordinates or just the x values?
Coordinates. So when they say, there's two words for this. It's called local max or relative max. And I mentioned them yesterday, but those are your peaks and valleys. Now if I want to find my local max, is everybody okay that my local max is going to be when x is 0? Can we see that from our chart? That's where we get our peak. And so anytime you're asked for a local max or a local min, you need a coordinate. And in this case, our local max is going to be, let's see, the x value is 0. Well, that's easy to plug in. So I'll plug in. Actually, where do I plug 0 in? Let's just make sure we get this right. What would happen if I plug 0 into the derivative? What are we going to get?
The 10.
We're going to get 0. Right? That's a flat. Oh, don't we have a flat spot at 0? If you have a flat spot at 0, when you plug it into the derivative, you're going to get 0 because you get a flat spot at 0, right? So anytime you want a coordinate, you got to make sure you remember to plug it back into the original function. 0 is pretty easy. All these go away, and I get a 5. Okay, where do I have a local minimum?
You want the coordinates or the x values?
Well, the where is just the x part. So where do I have a local minimum?
From
Negative
0
1 and 2.
Or between 0 and
-1 and 2.
-1 and
1
2, right? Everybody see we have a local minimum, we have a valley here, and we have a valley here. So if I'm looking for my local minimum, then I've got -1, and I've got 2 and something. I've got to find the y values. And so to find the y values, I'm going to plug -1 into my function, and that's not so bad. Let's see, that's going to give me 3 plus 4 minus 12 plus 5. Did I do that right? Yeah, I did. So what do I get?
0.
I'm going to get 0, right? Because that's 12 minus 12 is 0. And to find the y value of 2, I plug 2 in. So 16 times 3 is 48. Minus 32. What's that? 4. Minus 48 plus 5. I think that gives me a -27. Alright, because those go away, -32 plus that gives me -27. So,
No, 2 squared is 4. Minus 12. Oh, wait, no, I did not find that.
okay. Alright, so the first derivative test gives us 2 pieces of information. It tells us where something's increasing or decreasing. It also tells us where a local max and local min are, right? That's what happens in the first derivative test. Okay, but if you just have a bunch of polynomials, that's not very interesting. So we've got to change things a bit. What if I gave you x squared minus 4 to the 2/3?
You want us to make chart for that?
Oh, no, I'll do it. I mean, no. So our goal is, okay, I want to know my local, they're called local extrema, basically the local max and the local min. That's what I need. All right, so I need to find the local max and local min. How do I do that? Well, I want my first derivative chart. So the very first thing I need to do is, well, find my critical values. So find my critical values, I take the derivative, so that's 2/3 times x squared minus 4 to the -1/3 times 2x. Everybody okay with that? And, okay, well, probably clean this up a bit. So that's going to give me a 4x over 3 times x squared minus 4 to the 1/3. Now let's talk about critical values. Critical values, you're looking for 2 things. You're looking for where the derivative is 0 and
Undefined.
where the derivative is undefined. So where is this equal to 0? What values of x make this 0?
0 and...
Are we okay with 0? All right. So we're going to get critical values at x equals 0, because that's where the top equals 0, right? Because if you have a fraction, if you want to know where the fraction equals 0, you care where the top is equal to 0. If I want to know where it's undefined, what do I want?
The bottom.
0.
Where the bottom is 0, right? And so where's the bottom 0?
2.
2 and
Negative 2.
-2, right? So I have critical values at 0, 2, and -2. Everybody see how I got those?
Yes.
Right? Those are our critical values. And since once I found my critical values, now I'm going to do my chart. And so my chart has -2, it has 0, and it has 2, and I've got to find out what's happening in each interval. So I'm going to try a number over here. -1,000. Are we okay? 4 times -1,000 is a negative number? Okay. Are we okay? -1,000 squared is a fairly large positive number? And a fairly large positive number minus 4 is still going to be positive?
Yeah.
We take the cube derivative, it's still positive, so the bottom's positive. So negative over positive is negative, all right? Next, I want to find out what's going on here, so guess which number I'm going to pick between -2 and 0?
1.
Probably -1, right? Are we okay that 4 times negative 1 is going to be negative?
Well, that's easy.
Okay. You don't want to sneeze in a mask. Yeah. All right, so the top's negative, and then negative 1 squared minus 4, that's negative, and the cube root of a negative is still negative. So our bottom's negative. And so I have negative over negative is positive. And then I'm at 0. I'll pick 1 over here, so now I end up with positive over negative, which is negative. And if I pick a giant positive number, top's positive and the bottom's positive. So we get positive. And what I get out of this is, well, okay, it's decreasing, then it's increasing, then it's decreasing, and it's increasing. And when I look at this chart, is it easy to, it's easy to, it's not even worth asking the question, where is it increasing or decreasing, right? Because the chart gives it to us, right? But I am interested in where my local max and local min are. So I want to know my local max, and I want to know my local min. So if I'm looking for my local max, what x value is going to cause my local max? 0. So I need to plug 0 into my function. I'm going to plug 0 into the function. Looks like I get negative 4 to the 2/3. And we can clean that up. I mean, like negative 4 to the 2/3 is the exact same thing as negative 4, the cubed root of negative 4 squared. And negative 4 squared is 16, so this ends up being the cubed root of 16. Somewhere between 2 and 3. So this ends up being the cubed root of 16. All right, now let's talk about local mins. What x values give me local minimums?
Negative 2
Negative 2 and
and 2.
2. So negative 2, and then 2. Now let's see. If I plug a negative 2 into my function, what am I going to get?
0.
0. And if I plug 2 in, I still get 0. And if you're curious, here's what this picture looks like. I mean, just because you see arrows, don't imagine it's this nice, smooth thing.
Yeah, it's got
And the reason we know it's not nice and smooth is there's places where the derivative doesn't exist, right? So here's your picture. I don't want to actually spend the time to turn the projector on, but so at negative 2 and at 2 it does this, and the cross is up here. It ends up looking something like that.
pretty neat.
So notice we get the flat spot at 0. That was where the derivative was 0. But we also get little cusp at negative 2 and 2. That was where your derivative was undefined. Yes?
How come it's going in the positive range behind negative 2?
It's what?
Going to like the positive range.
Why is it going up?
Yeah.
Well, notice this thing says it's decreasing.
Oh.
Right?
Yeah.
Okay, all right. So this says I'm going all the way down. Also, you may not realize this, but you could actually tell from the original equation that nothing is going to be below the x-axis. And the reason you can tell, do you see this top thing is squared? And when you square stuff, aren't you guaranteed positive? So even though this says 2/3, there's the divided by 3 part, but the squared part is guaranteeing everything's above the x-axis. Yes? Yes. Well, I've avoided long enough. We got to do it. We got to do this with trig functions. And so there's good news and bad news. The bad news is, yes, are we going to have to do these questions with trig functions? Yes. Are they going to be on the AP exam? Yes. That's the bad news. The good news is they really just use sine and cosine. Right? I very rarely see anything with secant, cosecant, tangent, or cotangent. Most of the time they give you questions where they're asking, well, like in these types of problems, they stick with sine and cosine. Now we're on the interval from 0 to 2 pi, and I want to find my local extrema. I want to know where's my local max and where's my local min. So, what do you do first?
Find the important values.
Find the critical values, right? We're going to do our first derivative test, so that means take the derivative, so end up with f prime of x is equal to 1/2 minus cosine x. Take the derivative, set it equal to 0, and then we end up with cosine x is equal to 1/2. And this is kind of where I stopped. Here, I'll make cosine x equals 1/2. Where does cosine equal 1/2? Where is your x value 1/2? Well, our x value is 1/2 here and here, right? And so what's here? What angle?
5/3.
And what angle?
5/3.
5 pi over 3. Did that make any sense? Okay. Well, whoops. Of course, now I found my critical values. Now I have to do my little chart. And so we're going to start at 0. We're going to end at 2 pi. We're going to have pi over 3. And we're going to have 5 pi over 3. And now we need to check. Right? Here's our derivative, right? And so what I'm going to pick is something really close to 0, right? I need to check this interval, right? And really close to 0, well, let's see. Can we see that if we're really close to 0, cosine is pretty close to 1? And if cosine is pretty close to 1, 1/2 minus something pretty close to 1 is going to be negative. If I'm going to check this interval, I'm going to plug in pi. And 1/2 and cosine of pi is -1, so 1 minus -1 is positive. And then if I want to check this interval, that means we're back over here. And we're back to the spot where my cosine of my angle is really close to 1. So I end up with 1/2 minus close to 1 is negative. And so I find out that this is decreasing, increasing, decreasing. And if you're asked to find out, where's your local max? We have a local max at 5 pi over 3, and we're going to have a local min at pi over 3. Yes?
Why don't you do the... Oh, never mind. I was going to ask, why don't you do the 2 outside, and then I saw the 0 to 2 pi.
Oh, the 0 to 2 pi. That was a restricted one. Okay. And our last slightly painful one.
3 minutes.
I have 3 minutes.
Yes, sir.
Why didn't I write this down? I thought I had it. Ah. Yes.
I know I already kind of asked about this earlier, but if we know there are no zeros in the...
So when you're doing your chart of right now, the examples I'm giving, they alternate. So you think once you know the first one, you just keep going. They don't always do that. And it's not always obvious that they don't always do that. With polynomials, it is. But with certain trig functions, it's not. When we start dealing with exponential and log functions, it's not. So the safe thing to do is check. Are there shortcuts? Yes. And, well,